Hello and a warm welcome back to my YouTube channel. I trust you are all well, in good spirits and ready to see the most beautiful equation, perhaps, in the IB Chemistry data booklet. Which one do I refer to? Well, delta G naught is delta H naught minus T delta S naught. Where's the naught? I left it off. What does it mean? Standard conditions, okay? 298 Kelvin, 1 atmosphere. You should all know that. Why is this so beautiful that IB can ask 1, 2, 3, 4 quantities to be calculated from one simple equation? We can ask for the entropy, the enthalpy, the Gibbs free energy, which marries together those terms, both enthalpy and entropy, where we are juggling the thermodynamic properties and direction of a reaction. This is why this equation is so useful and perhaps is the most frequently present in the data booklet in its 4 different forms. We know that if delta G is negative, we call the reaction spontaneous. It doesn't mean it's going to happen. We also need to take account of the kinetics of the reaction, and that will only happen if the energy is greater than or equal to the activation energy and molecules collide with the correct orientation, as we all know. If it is positive, however, it is definitely non-spontaneous. It's not going to happen. That could be temperature dependent. We'll come to that later in this video. If delta G is 0, that means that we are at equilibrium. So if delta G is at a minimum, we are approaching equilibrium, whereas we all know Kc equals Q. The unit for entropy, that beautiful term, which is a measure of disorder in the system, so if it's positive, it's more disordered, if it's negative, it's less disordered, are joules per Kelvin per mole, as we see on the bottom of the screen. This does bring together our knowledge of thermodynamics. And if we're calculating the entropy, that's the sum of the entropy of the products minus the sum of the entropy of the reactants. If it's an increase in entropy, we call that favored. The universe likes an increase in disorder. If it's negative, it is disfavored, unfavored. Choose your adjective. It's less likely to happen. The universe also enjoys, from a thermodynamic point of view, that the enthalpy will be exothermic or negative, something much more likely than an endothermic reaction to happen. So we can calculate T, delta G, delta H, or delta S. So in fact, any of the quantities in delta G, delta H minus T, delta S, these can be asked as a question. You just need to make each of those quantities the subject of the equation by basic transposition, which we can all do, right? Yes. So, potential pathways that they can ask. I'm going to keep it to delta H minus T delta S. I know that delta G is minus RT ln Kc and delta G is minus NFE naught as well. However, that will be the subject of a different video. Remember, negative delta G is spontaneous. That means it's likely to happen. Doesn't mean it's going to definitely happen. If it's more negative, then it's more likely to happen. If it's less negative or more positive, it's less likely to happen. How do we work out delta H then? What's the delta H term? Well, we can use formation data. Formation data, use a Hess's law cycle. We can do the enthalpy of the products minus the enthalpy of formation of the reactants. Remember, that holds true for formation data. For combustion data, enthalpy of combustion, it's the other way around. You can draw the Hess's law cycle or do the sum of the reactants minus the sum of the products. Delta H, as you know, we can also use average bond enthalpy data, and I was always taught that this is breaking, the sum of the breaking, take away the sum of the making. You've probably been taught it as the sum of the enthalpy of reactants minus the sum of the enthalpy of the products. Or of course we can do an experiment and we can extrapolate that line to get delta T, which is sometimes asked in a question, and then we get Q, because Q is MC delta T and delta H is Q over N. So that's 1, 2, 3, 4 ways. We could also use a Born-Haber cycle to work out delta H. So there's 5 ways that we can get the enthalpy for the reaction. Any of those approaches, the IB is more than at liberty to use as a route to answering questions of this nature. Remember, just to repetition helps it stick in the human brain, temperature must be in Kelvin. They could give you in degrees C, then ask you to add the 273.15. Seems a bit tedious, but it's a potential. They could ask you to do that. Okay. Entropy, remember, is the sum of the entropy of the products minus the sum of the entropy of the reactants. That's the same as the enthalpy of formation data. But the key thing that students get wrong is, yes, you've guessed it. Enthalpy is always given in kilojoules per mole. Entropy is always given in joules per mole. So you're either going to have to divide your joules per mole entropy quantity by 1000 or times it by 10 to the minus 3, or do the converse with the enthalpy quantity to make sure those units match when you are using delta G is delta H minus T delta S. Again, why is this a beautiful thing? Because it balances all the driving forces for the reaction. And classically, when the IB have got you to work out this question or work out a numerical sum, which will be in the next part of this video, they will ask you about when is a reaction spontaneous, when is it non-spontaneous, for which combination of enthalpy and entropy is a reaction going to be spontaneous. As I mentioned in the preceding segment to this video, that if we increase entropy, the universe likes that, and it's exothermic, it's giving out heat, that's always going to be spontaneous. So if the enthalpy is greater than zero, so it's going to be endothermic, and delta S is negative, because of the calculation delta G is delta H minus T delta S, it's going to be non-spontaneous at all temperatures. That's the bottom left quadrant of this diagram here. If delta G is less than 0, it's negative, so delta H negative, delta S positive at all temperatures. But if delta H is negative and delta S is not, then it's only going to be spontaneous at low temperature. I always kind of put those numbers in my head into the equation and see what I get. It does take a little bit of working out. The main issue with students answering these questions is the units conversion, which I mention again here, joules and kilojoules. Don't be caught out by that in a problem. So this old Gibbs chap is quite a big deal. It occurs a few times in your data booklet. And we've got delta G is delta H minus T delta S. Delta G is minus NF E naught. Remember, E naught needs to be positive for the standard electrode potentials. That will be a subject of a different video. And a video already on my channel relates delta G to minus RT ln Kc. If you look around the internet, you can relate to delta G as delta G naught plus RT ln Q, Q being the reaction quotient, but the IB have never asked that. So let's move on. So we finally get to how to answer a question that's given, and this is inspired by a previous IB paper. We have hydrogen and iodine in equilibrium with hydrogen iodide. It's a homogeneous equilibria because that's what's on the syllabus. Okay, if you ever see any other states, solid, liquid, etc., just ignore them. They're not going to appear in the Kc expression. The first part is always some low-hanging fruits to make you feel better. They are kind-hearted at the IB. State the Kc expression. So there's 2 lots of Hi in the balanced equation. The coefficient is 2, so we square the concentration of hydrogen iodide. We divide that by the concentrations of hydrogen and iodine, both in their gaseous states. The IB will give us 1 mark for that, and we all feel warm and fuzzy inside. So now we can go on to the next part of the question. Next part is calculate the entropy. Remember, that's the delta S term. Given that, and they will normally give you a table of values. Sometimes they will direct you to the data booklet. You have to do a little bit of legwork to go and find the values. Just always be doubly careful, triply careful, quadruply careful that you are looking at the correct state and the correct reactant or product. Units again, joules per Kelvin per mole. Joules, 130.6 hydrogen, 116.1 iodine, 206.6 for the hydrogen iodide. We've already calculated or done the expression for Kc, so it's now trying to get us on to the next part. And we know that the entropy of the reaction is the sum of the entropy of the products minus the sum of the entropy of the reactants. Don't forget to double, because there are 2 moles of hydrogen iodide, so you have to double your 206.6, which is the entropy of hydrogen iodide. And take that away from the sum of the reactants, 130.6, 116.1, you should get 116.5. Don't forget the units, forget the mark. 166.5 joules per Kelvin per mole. Tick, the IB are very happy. It's then going to go on. If I change the state of one of these reactants or products, what's going to happen? Well, if I change the states, I'm going to change the entropy, aren't I? I don't think I changes the entropy. So if iodine was a solid, not a gas, what would be the effect on the entropy of this reaction? Well, you all know that a gas has more entropy than a solid. Okay, the gas has more ways of ordering the energy, or is more disordered, if you like, than the solid is. So will the entropy be lower? Well, yes, of course it will be lower. So there's less entropy because a solid is a more ordered state. At the end of this question, it's going to ask us to calculate a value for delta G. So finally, we get onto the equation that we've been focusing on during this video, where delta G is delta H minus T delta S. It gives the units in the question, just so no teachers can complain that they didn't make that abundantly clear when the examiner's report comes out later in the year. It tells me the temperature, it's 298 K. So using the data booklet, delta G, delta H minus T delta S, delta H was given in the question, so we're just reading that from the previous part in the text, which was 53 kilojoules per mole, so it's an endothermic reaction. Minus T, Kelvin, 298, don't forget the units conversion, 166.5 becomes 0.1665, and now that's in kilojoules per mole per Kelvin. That means my delta G is going to equal quite a small number really, it's 3.4 kilojoules per mole. That's positive 3.4 kilojoules per mole. So this is actually a non-spontaneous a non-spontaneous reaction at 298 Ks. Then asks me to calculate the Kc value. So we can use the relationship delta G is minus RT ln Kc and rearrange for ln Kc, and then finally solved for e to the power of the function on the right hand side. So ln Kc is 3.4 by 10 to the 3 joules, remember I get joules, divided by, this is delta G is minus RT ln Kc, rearranged for ln Kc, divided by the universal gas constant, which is 8.31, times our T. So R and T, R times T is basically the kinetic energy of the system. If ln Kc is minus 1.37, then Kc is e to the exponent of minus 1.37, which I get to be 0.25, using delta G is minus RT ln Kc, which is in your data booklet. The final use of this equation is calculating the temperature at which a reaction actually becomes spontaneous. So T will vary, and obviously has a big effect. It's going to be quite a big number at standard temperatures that we find in a laboratory. Here I've used ammonia. It's a reverse of the synthesis you've probably seen. Normally it's nitrogen and hydrogen in equilibrium with ammonia. Now we've got ammonia in equilibrium with nitrogen and hydrogen. It's just the reverse. So the delta H would be the Kc, will be the reciprocal of that original relationship. It gives me delta H, 177.8, and it gives me delta S. Both of them are in kilojoules per mole, so that's great. Very kind of them in the question. So what's delta G? Well, if delta G is delta H minus T delta S, and we want to know the temperature at which this reaction will actually occur. We're given 177.8 minus the 298 times it by the 0.1607. That's giving me the delta G at 298K. I make that 129.9 kilojoules per mole. So that means it's non-spontaneous. It's not actually favoured at 298K. So how do we solve for at what temperature will this reaction actually begin to happen by itself? Because that's a key thing to know if you're working in industry, if you're working in the pharmaceutical industry, petrochemical industry. We want to make the minimum use of energy to actually make the process happen, so we don't spend too much money that we don't need to actually do, and we can make the maximum profit from our product. Well, when is it going to become spontaneous? It's going to become spontaneous when delta G becomes negative, and the tipping point between positive and negative is obviously at 0. So if delta G approaches 0 or becomes 0, that will give us the temperature at which the reaction will begin to become spontaneous. So let delta G equal 0. So now 0 is delta H minus T delta S. Mic T, the subject. So you've got enthalpy divided by entropy will give us a value in Kelvin for the temperature at which the reaction becomes spontaneous. In this case, that's 1106 Kelvin. Hope you found today's video useful. Comment, like, smash that subscribe button. Have a great day. Thank you for listening.